Hello, welcome back to the online class on electron devices and circuits. And this class we're going to see about the transition capacitance and the diffusion capacitance of a p-n junction diode. In the earlier classes we saw about the p-n junction diode structure, its operation and VI characteristics, and now coming back again to the p-n junction structure, we need to much more understand on the transition capacitance and diffusion capacitance. When how does these p-n junction diodes form as a capacitance and so, and we'll describe both of this. So generally when you take a p-n junction diode, so if this is a p-type p and n layers, this is p and n layer, you have a diffuse layer formed in between, and this diffusion layer is of high resistance and it is actually as an insulator. This has a very high resistance, or we also call it as an insulator. So since due to this insulation the conduction is not generally possible unless the insulator layer or the diffusion layer is broken down. So that's what we saw last time. So now it is also very clear that in electron devices they are inherently sensitive to very high frequencies. They are inherently very sensitive to high frequencies, and also certain shunt capacitance are neglected, or actually these shunt capacitors are ignored at lower frequencies. So these are very common in semiconductor devices. So in p-n junction diodes there are two types of capacitors possible, or actually that happen that comes during the operation. That is, one is the transition capacitance, and another one is diffusion capacitance. So this transition capacitance usually appears during the reverse bias, and the diffusion capacitance appear during the forward bias. So why do we call it as a capacitance? You know what is a capacitor is all about. It's a two parallel plates separated by an air medium which is an insulator. So usually it looks like this. You have a gap between the two parallel plates. These are the parallel plates and the gap. So this is how looking. Similarly, when you compare this diagram with this p-n junction diode, you can probably see that this region which is insulated, you have these two places. One here is like p type and this is n type, so this becomes almost looks like a capacitor. That's why we mean it is a capacitor. So during this operation we have either transition capacitance or diffusion capacitance are formed in between this. Earlier, before that, for any p-n junction diode, the capacitance conditions vary with respect to this. That is, during equilibrium you have an equilibrium capacitance, and on the forward bias I have the diffusion capacitance, and when the reverse bias you have transition capacitance. So in the equilibrium it means that it's not conducting, that is there is no conduction during no conduction, or we'll say that is nothing, no voltage is applied, so no input voltage. During no input voltage this happens, and this is under the forward bias condition, and this is reverse bias condition. Okay, so these are the various three types, and we will see in descriptively we'll see about the three cases, how does it appear. So let me start with an equilibrium capacitance at first, so that you can easily understand the rest of the two types of capacitance. Equilibrium capacitance. So let us see how this capacitance value is given at the equilibrium condition of a PN junction diode. At equilibrium condition, what happens is like you have a diode, PN diode here, PN diode. It is not connected to any voltage here. So this is the diffusion layer formed between this PN junction. So what happens is like there are some charges, you know that, right? So here there are majority carriers or holes, that is the positive charges present over here, and you have the negative charges present in the n type. You don't have the majority carriers here, right? So there are some charges. Let me take it as the charges, that is with respect to, right, is q minus and q plus. That is because these holes or free holes can accept, this is an acceptor side, this can accept the electrons, and these n type are having too many electrons which can donate it. So this is an acceptor region, and this is a donating region. So this is called as an acceptor, and this is donor, right? So eventually we can write the that is a charge values, that is the modulus of q minus should be equal to the modulus of q plus, the charges that is between your acceptor and the donors. The charges are equal, they are not they are not connected to any voltage source. So they have equal number of charges, both in the negative and the positive. All right, so when I expand this expression for q minus and q plus, you have this is a small q, a x p o n a is equal to x a q a x n o n d. So let me explain you what is this. Q is nothing but the charge. There is a q is the charge in these two, and a is the cross sectional area, and xpo is nothing but the distance of the width, that is the diffusion layer width has been extended to both the sides of the positive and the negative side. So one side I am taking that for the p type, that is I am going to separate as 2. This is the middle point, and here you have x p naught, and this is x n naught. So combined is the x p naught plus x n naught will give you the total diffusion length. Okay, so this is how it has been separated. So x p naught is the distance or the diffusion length width at the p type region, and x n naught is the diffusion layer distance or the length at the n type region. And you have Na is the number of acceptors, and number n is the number of donors. So from this equation, it is very simple, like q get cancels, a also get cancelled, and from this you can write that x no divided by x po can be given as Na by nt. So this is an expression can be derived from here. And also the width, I have, as I told you, width of the depletion layer capital W. I'm giving the width of the depletion layer as a capital W, which is equal to x no plus x po. So now we can understand from the diagram what I told you, like xpo and xpo combines to form the total diffusion length. So and if using all these things, the xp from let me take it as this equation number 1. I'm going to substitute this equation number 1 in the equation number 2. So 1 can also be written as that x no can be given as Na by Nd into xpo. So when I substitute this equation in the equation number 2, my 2 can be written as W is equal to, instead of x no I can write as Na divided by Nt into xpo plus xpo. So I'm not replacing this. So here we can find xpo is common, so we have 1 plus Na by Nt. So this is the width, can also be given in this form. So for the simplification, we can write xpo into, that is I'm taking LCM, so nd plus na divided by nd. So this is how it is looks like, and this is the width. So I'll rewrite this equation, that is into xpo into nd plus na divided by nt, right? So upon on this, what is xpo from this equation? Let me again come and write what is xpo. So xpo can be written as w into nd divided by na plus nt, right? So xpo can also be written as like this. So I'm taking this as one equation. So this is equation number 3, which gives the xpo value. So this xpo value can be used further on other equations to be done. And similarly as xpo, now we can write what is the value of xno. So similarly, let us directly write it as xno is equal to w times na divided by na plus nd. Okay, so this is the equation. This two, the third equation and the fourth equation gives you the value of the length or the width of the depletion layer towards the p type and the n type, right? And in general, the capacitance at the equilibrium condition, or in generally, what is a capacitance? So capacitance equation can be given as C is equal to epsilon naught A divided by T. So where epsilon naught is nothing but what? Epsilon naught is the permeability, A is the cross sectional area, and D is the distance of the parallel plate. So the parallel plate. So this is the general equation. And when you come to the p-n junction diode, so for p-n diodes that usually at equilibrium, let me write it as Cj, which is the junction capacitance. I mean Cj. I'll take it as epsilon Si, because we are using a silicon semiconductor, so I'm representing it as epsilon Si. A divided by the D is nothing but the width of the depletion layer, or this width of the parallel plate. So that is the depletion layer here. So I'm putting it as capital W. And also this W expression for the p-n junction diode can be also given like this: 2 epsilon Si by Q into 1 by Na plus 1 by Nd into V naught, the whole root. And here this V naught is nothing but the built-in potential, or we call it as it is the junction potential. So now we'll write that expression in detail. So let us substitute the value of W in this above equation Cj. So now therefore your Cj can be given as epsilon Si into A divided by the W, the value I'm going to write it here. So it is 2 epsilon Si divided by Q times 1 by Na plus 1 by Nd into V naught, and it's a whole root. So in the common cases, we can cancel the epsilon Si here and epsilon Si. So if I cancel it here, I'll get back root epsilon Si. And in that case, when I return this equation, we can write it as A into Q epsilon Si divided by 2 into Na Nd divided by Na plus Nd into V naught, right? So this is the further simplified equation. So what I'm going to do now here is I'm going to take this 2 numerical value of 2 outside, and let me show you how does it come. Like a divided by 2, since I have taken the 2 outside, you have to multiply and divide by, like, you have to divide by the values respectively. So you have 2 q epsilon si into Na Nd divided by Na plus Nd into 1 by V naught, right? So this is the actual expression. So we can say that the equilibrium capacitance of the PN junction diode can be given by this expression, and based on this expression the transition capacitance and also the diffusion capacitance can be derived. So further on the transition capacitance, again we can directly write it. So the next, the second one, I told you this is what is equilibrium capacitance. I'll write it here, equilibrium capacitance. So now transition capacitance. So transition capacitance can be easily given by this value. Like in transition capacitance, what happens is it is in the reverse voltage condition. That is, the PN junction diode is it is connected to the, that is, anode of the PN junction diode is connected to the negative and the cathode is connected to the positive. So what happens, your depletion layer keeps increasing. So on keeping on increasing that value, the voltage expression value will change. So what happens actually is we can represent it as CT can be given as A by 2 the whole root 2q epsilon si Na Nd divided by Na plus Nd into 1 by V naught plus Vr, because the voltage we are giving, that is the depletion layer, is increasing. So we are going to add the reverse voltage Vr, where Vr is a reverse voltage. So this value we have added to the V naught, which is the junction potential. So this is the expression, and from this expression it is very clear, like we can see that, right? I show you these values except this V naught, this is what is nothing but your Cj. Okay, so let me take in that expression. If I take this V naught outside from this, which common from this expression, it will be given as A by 2 the whole root 2q epsilon si Na Nd by Na plus Nd. I am taking the V naught outside, so it will given by 1 divided by, if I take the V naught, by 1 plus Vr by V naught. Okay, so this is how it's look like. So I can write this expression, that is A, all these expression as Cj. It is Cj times 1 divided by 1 plus Vr by V naught, which is nothing but, which is supposed to come in the square root. So this is the CT. In general, the expression for CT can be given as Cj 1 divided by 1 plus Vr by V naught the whole power n. And what n means is, the n value of n will be 1 by 2 for step graded junctions, and n value will be 1 by 3 for linear graded junctions. So you can probably use this, either two of this equation, where you can know, by knowing the value of n, you can substitute on this equation and give it. So especially you should be very much being required for knowing the value of Cj and the W expression, which is more important in the finding the value of the transition capacitance or the diffusion capacitance. The third one, there's the last one, is the diffusion capacitance. So diffusion capacitance, we will denote it as CD. In diffusion capacitance, it is usually in the forward bias condition. So when the forward bias there is the condition for the PN junction, the depletion layer will keep decreasing. Okay, then at one point it diminishes and it starts to conduct. So initially here, with the expression of the width of the depletion layer, from the general expression we can give it as 2 epsilon Si divided by Q 1 divided by Na plus 1 divided by Nd into V0 minus Vf, because here the width of this is going to decrease. So that's why I am subtracting the forward voltage, where Vf is the forward voltage from the junction potential. So with this expression, it is easy again to find this value of CD. So what is that? CD is nothing but epsilon Si into A divided by the W, the value what I have to substitute the same value here. So it is nothing but 2 epsilon Si by Q 1 by Na plus 1 by Nd times V0 minus Vf. So whole root. So similar way, have to simplify again the same way I'm going to do it. So I'll have it A here into I'll take again the same thing, say A divided by 2. We'll take the 2 outside here, so we'll left out with this is 2q epsilon Si Na Nd divided by Na plus Nd into 1 divided by V0 minus Vf. So again, to represent in the value of the equilibrium capacitance, I am going to replace this equation in this way, that is 2q epsilon Si into Na Nd divided by Na plus Nd into 1 by V0. I am taking it as common, so that I will arrive with 1 divided by 1 minus Vf by V0, the whole root. So can again see this expression is very similar to Cj. So I can write as Cj into 1 divided by 1 minus Vf by V0, whose I am having the root of it. Okay, so by general expression, as I already told you, either you can have it as in the square root, or you can in general your CD can be written as Cj times 1 divided by 1 minus Vf minus V0, the whole power n, and n, as I told you, it is 1 by 2 for step graded junctions, and n will be 1 by 3 for linear graded junctions. So these expressions are very clear about that transition capacitance and the equilibrium capacitance for the PN junction diode. So we should remember how these expressions are given, and main thing is, like, you should know the equation for the width of the depletion layer in just a general equation, and how it changes. That is just a value of the voltage, forward voltage will be subtracted at the case of diffusion capacitance, and a reverse voltage will be added in case of a transition capacitance, and based on this you have a simple derivation. So this is how the derivation goes, and you can remember this for the if you have to do for some problems, you have these formulas to be used. Thank you.